What if I told you there's a diesel engine so tough that it once ran for 18,000 hours straight without a rebuild? That's over 2 years of continuous operation at full throttle. While Ferrari was crafting Joule-like V12s and Porsche was perfecting their air-cooled flat sixes, a bunch of engineers in Peoria, Illinois were building something entirely different. Something that would embarrass purpose-built racing engines, dominate endurance competitions, and redefine what bulletproof really means. This is the story of how Caterpillar's Bulldozer engines became the most unlikely performance heroes in motorsport history. Horton, picture this. It's 1979 at the 24 Hours of Le Mans. The Porsche 935s are screaming down the Mulsanne Straight at 200 miles per hour, their turbocharged engines pushed to the absolute limit. In the pits, factory teams have spare engines ready, knowing their highly strung power plants might not survive the full distance. Meanwhile, in a corner of the paddock that nobody's paying attention to, there's a diesel-powered car with an engine that started life-pushing dirt. By the time the checkered flag falls, that Bulldozer engine will still be running perfectly, while million-dollar racing engines lie scattered in pieces across pit lane. None. Here's what most people don't understand about Caterpillar engines. These weren't just tough engines. They were engineering monuments to a completely different philosophy. While every other manufacturer was chasing power-to-weight ratios and specific output figures, Caterpillar engineers were asking a different question. What if we built an engine that simply couldn't break? And to understand why a Bulldozer engine could embarrass purpose-built racing power plants, we need to travel back to 1925. Caterpillar had just formed from the merger of Holt Manufacturing Company and CL Best Tractor Company. The world was mechanizing rapidly. Construction projects were getting bigger, mining operations were going deeper, and equipment was being pushed harder than ever before in places where a breakdown didn't just cost time, it could cost lives. The early diesel engines of the 1920s were unreliable monsters. They'd crack blocks, throw rods, and generally self-destruct with alarming regularity. A typical industrial diesel of that era might last 500 hours between major rebuilds if you were lucky. For comparison, that's about what a modern car engine does in 15,000 miles of normal driving. Caterpillar's customers needed better. A bulldozer working in the Panama Canal expansion couldn't afford to break down. A generator powering a remote mining operation had to run continuously for months. Failure wasn't just expensive, it was potentially catastrophic. So Caterpillar's engineers did something radical. They started with the assumption that every component would be abused, overstressed, and poorly maintained. Then they designed around that assumption. Where other manufacturers used cast iron, Caterpillar used forged steel. Where others specified maintenance every 100 hours, Caterpillar built engines that could run for 1,000 hours between services. The design philosophy was simple but revolutionary. Overbuild everything, understress everything, and assume the worst-case scenario is the normal scenario. The real breakthrough came in 1931 with Caterpillar's first diesel engine designed from scratch, the D9900. This wasn't an adapted gasoline engine or a licensed design from Europe. This was pure Caterpillar engineering, and it established principles that would define their engines for the next century. The crankshaft was forged from a single piece of steel, then machined to tolerances that were considered excessive for the era. The main bearings were sized to handle 3 times the maximum load they'd ever see. The cooling system could dissipate enough heat to keep the engine happy in Death Valley at noon or the Arctic at midnight. But here's where it gets interesting. The D9900 wasn't particularly powerful by the standards of the day. It made about 75 horsepower from 1,090 cubic inches. That's less than 0.07 horsepower per cubic inch. A contemporary gasoline engine could make 4 times that specific output. Racing engines of the era were approaching 1 horsepower per cubic inch, but the D9900 could make it 75 horsepower continuously, not for minutes or hours, but for months, years even. The engineering that went into these engines was obsessive. Take the 3306 engine that debuted in 1973. This was a 10.5-liter inline-six that would become legendary in ways Caterpillar never imagined. The block was cast from high-grade iron with walls thick enough to stop a bullet, literally. The cylinder sleeves were replaceable wet liners made from centrifugally cast iron, heat-treated to a specific hardness that balanced wear resistance with machinability. The pistons were aluminum with steel inserts at the ringlands, designed to expand at exactly the same rate as the cylinder walls to maintain perfect clearances across a temperature range of -40 to +250 degrees Fahrenheit. The crankshaft alone was a masterpiece of paranoid engineering. Forged from 4140 steel, it was nitrited for surface hardness, then precision ground to tolerances of plus or minus 0.02 inches. The journal radii were specifically calculated to minimize stress concentrations. The counterweights were designed not just to balance the rotating assembly, but to actively dampen harmonic vibrations that could cause fatigue failures after thousands of hours. Every single 3306 crankshaft was magnafluxed and X-rayed before installation. A microscopic crack that would be acceptable in a passenger car engine meant immediate rejection, and then the fuel system was equally overbuilt. While automotive diesels of the era used distributor-type injection pumps with a single high-pressure element, the 3306 used individual pump and injector units for each cylinder. Each injector was a precision instrument capable of delivering fuel at pressures up to 20,000 psi through holes smaller than a human hair. The injection timing was controlled by a camshaft ground to such precise tolerances that Caterpillar had to develop their own measuring equipment because nothing commercially available was accurate enough. And now, you might be wondering why any of this matters outside of construction sites. The answer came from an unexpected source: endurance racing. In the late 1970s, fuel economy became a critical factor in long-distance racing. The oil crisis had made fuel efficiency suddenly sexy, and race organizers were introducing consumption limits. Teams started looking at diesel engines as a way to go further on less fuel. But racing diesels had to be light, which meant aluminum blocks and minimal cooling systems. They were fast, but fragile. Then, someone had a crazy idea. What if instead of making a diesel engine act like a racing engine, they took an engine that was already bulletproof and just made it fast enough? Enter the Caterpillar marine engines. These were essentially industrial engines modified for boat use, with higher power outputs thanks to better cooling and the ability to run at constant high RPM. The 3208 V8 marine engine, in particular, caught the attention of creative race engineers. The 3208 was a 10.4-liter V8 that made about 375 horsepower in marine trim. Not impressive by racing standards, where turbocharged Porsches were making 600 horsepower from 3 liters, but the 3208 could make its 375 horsepower forever. It had been designed to push fishing trawlers through heavy seas for 10,000 hours between overhauls. A 24-hour race? That was barely a warm-up. Then the first serious racing application came from an unlikely source: Theodore Racing. Teddy Yip's team was known for running unconventional entries, and in 1979 they entered a March Caterpillar 79C in selected Can-Am races. The engine was a lightly modified 3208, making about 425 horsepower. The competition was running turbocharged Chevrolets making 800 horsepower. On paper, the Caterpillar didn't stand a chance. But racing isn't just about peak power. It's about average speed over distance. And this is where the Caterpillar's industrial heritage became a massive advantage. The engine didn't need to be babied. It could run at maximum power, lap after lap, without overheating. The drivers could stay flat on the throttle through sections where others had to lift to manage temperatures. The engine's massive torque, over 900 lb-ft, meant less shifting, less stress on the transmission, and more consistent lap times. The real shock came at the 1980 24 Hours of Le Mans. Two privateer teams entered diesel-powered cars using Caterpillar engines. The first was a modified 3208 in a Rondo chassis. The second was something even more audacious, a 14.6-liter 3406 truck engine stuffed into a purpose-built prototype. The 3406 was an inline-six designed for 18-wheelers, making about 425 horsepower, but over 200 lb-ft of torque. It weighed nearly 2,000 pounds, more than some entire race cars. And then the establishment laughed, until qualifying. The Caterpillar-powered cars weren't fast on outright pace, but they were incredibly consistent. While other teams were managing temperatures, watching oil pressure, and nursing their engines, the Caterpillar teams just drove flat out, hour after hour. The 3406, in particular, was a revelation. It used so little fuel that it could run nearly 4 hours between pit stops, almost double what the gasoline-powered prototypes could manage. And let me put that in perspective. A typical Group C prototype of that era would consume about 60 liters of fuel per 100 kilometers at racing speeds. The Caterpillar-powered car? It was using 28 liters per 100 kilometers, while making competitive lap times. The engine wasn't working hard. It was loafing along at what would be considered light load in a truck application. The attrition rate at Le Mans in 1980 was brutal. Of 55 starters, only 25 finished. Factory Porsche 935s expired with blown turbos. The works Ferrari 512 BBLMs suffered various mechanical failures. The BMW M1 Pro cars dropped out with overheating issues, but both Caterpillar-powered cars were still running at the finish. The 3406-powered car finished 12th overall, completing 298 laps. For context, it had covered over 2,500 miles at racing speeds with an engine designed to haul freight. The technical reasons for this reliability were rooted in Caterpillar's design philosophy. These engines operated at specific outputs that would be considered pathetic by racing standards. The 3406 was making about 29 horsepower per liter. A contemporary Formula One engine was making 150 horsepower per liter, but that meant the Caterpillar was essentially unstressed. The pistons, rods, and bearings designed to handle 100,000-pound loads in a truck were barely breaking a sweat pushing a 2,000-pound race car. And yet, the cooling systems were equally over-designed. A 3406 in a truck needed to dissipate heat while pulling maximum load up a 6% grade in 120-degree heat. At Le Mans, running on a flat track in 70-degree weather, the cooling system was operating at maybe 40% capacity. The engines ran so cool that teams actually had to restrict airflow to get them up to optimal operating temperature. The oiling systems were designed for engines mounted at angles in off-road equipment, bouncing over rough terrain. In a race car on smooth tarmac, oil starvation was physically impossible. The oil pumps could flow 50 gallons per minute, enough to fill a bathtub in 3 minutes. The oil galleries were sized to maintain pressure even with worn bearings after thousands of hours of operation. But the real secret weapon was the injection system. Caterpillar's unit injectors were mechanically controlled, incredibly precise, and basically indestructible. While other diesel race engines struggled with injection pump failures from the high-pressure cycles of racing, the Caterpillar injectors just kept firing perfectly. They'd been designed to operate in engines ingesting dust, moisture, and contaminated fuel. Clean racing diesel was like a vacation. The durability advantages went beyond just finishing races. Teams discovered they could run entire seasons without rebuilding the engines. A typical racing engine might need a complete rebuild after 24 hours of competition. The Caterpillars were checked with a compression test and sent back out. One privateer team ran the same 3208 engine for 3 consecutive seasons of endurance racing without opening it up. When they finally did strip it for inspection, the wear on the components was barely measurable. This led to an unexpected economic advantage. While factory teams were spending millions on engine development and rebuilds, privateer teams could buy a used Caterpillar marine engine for $15,000, modify it slightly, and be competitive. The entire engine program for a season might cost less than a single rebuild of a Cosworth DFV.10. The performance modifications that teams did make were relatively simple. Higher flow exhaust manifolds, modified injection timing, upgraded turbochargers on some versions, but the fundamental engine remained stock. Teams learned that trying to extract significantly more power usually resulted in the only thing that could kill a Caterpillar engine: human error in modification. One team learned this the hard way when they tried to increase the red line from 2,800 RPM to 3,500 RPM. The engine, which had run perfectly for 2 seasons, threw a rod through the block after just 20 minutes. The autopsy revealed that the failure wasn't from weak components but from harmonic vibrations at the higher RPM that the engine was never designed to encounter. Run within its design parameters, the engine was indestructible. Push beyond those parameters, and you discovered why Caterpillar set them where they did. The success of Caterpillar engines in racing led to some interesting developments in other motorsports. Tractor pulling, where modified farm equipment compete to drag weighted sleds, became dominated by Caterpillar power. The engines could handle boost pressures that would instantly destroy other diesels. Teams were running 100 psi of boost through 3406 engines, making over 2,000 horsepower. The stock bottom ends handled it without modification. Indestructibility and offshore powerboat racing saw similar adoption. The combination of massive torque, fuel efficiency, and absolute reliability made Caterpillar engines perfect for long-distance ocean racing, while high-strung gasoline engines were failing from the constant pounding of waves. Caterpillars just kept churning. One team won the Miami-Nassau-Miami race with an engine that had over 5,000 hours on it from commercial fishing use. Even land speed racing saw Caterpillar power. The massive torque and ability to run at wide-open throttle for extended periods made them perfect for the salt flats. A streamliner powered by a twin-turbocharged 3408 V8 set a diesel speed record of 237 mph in 1987. The engine made its record runs, then was installed in a mining haul truck where it ran for another 15,000 hours. The technical innovations that made this possible were revolutionary for their time. Caterpillar was using plateau honing on cylinder bores in the 1960s, a technique that wouldn't become common in automotive engines until the 1990s. They were using finite element analysis for stress modeling when most manufacturers were still relying on trial and error. Their metallurgy was so advanced that they had their own steel specifications that suppliers had to meet. The 3500 series engines that debuted in the 1980s took this philosophy to extremes. These were available as V8s, V12s, and V16s with displacements up to 78 liters. The V16 version could make 3,500 horsepower in industrial trim, but it was designed to do it continuously for 30,000 hours between overhauls. The crankshaft alone weighed 800 pounds. The engine consumed oil not because it burned it, but because the specification called for oil changes every 500 hours, and it held 50 gallons. In end, what made these engines truly special wasn't just their durability, but their consistency. A Caterpillar engine would make exactly the same power on our 10,000 as it did on our 1. The wear patterns were so predictable that maintenance could be scheduled years in advance. Performance degradation was essentially zero until wear limits were reached. Then components were replaced, and the engine continued for another cycle. This consistency made them perfect for applications where reliability mattered more than outright performance. Standby generators for hospitals and data centers used Caterpillar engines because they would start instantly after sitting for months and run at full load without warm-up. Military vessels specified them because battle damage that would cripple other engines might only reduce a Caterpillar's output slightly. The racing applications revealed something else interesting about these engines. They were incredibly smooth. The massive rotating assemblies and careful balance meant vibration was almost non-existent. Drivers reported that Caterpillar-powered race cars were less fatiguing to drive over long distances. The torque delivery was so linear that throttle modulation became instinctive. But perhaps the most impressive aspect was their tolerance for abuse. Racing teams discovered that Caterpillars would run on almost anything combustible. One team, stuck with contaminated fuel at a race, mixed in automatic transmission fluid to thin it out. The engine ran perfectly. Another team accidentally filled their tank with jet fuel instead of diesel. The Caterpillar didn't care. It actually made slightly more power. The engines would also run with spectacular mechanical damage. There are documented cases of Caterpillars continuing to operate with cracked pistons, broken valve springs, and even holed blocks. One marine engine ran for 6 hours with no oil pressure after a line ruptured, finally ceasing only when it ran out of residual oil in the galleries. When rebuilt, only the bearings needed replacement. This tolerance came from the fundamental overbuilding. Every clearance was designed to accommodate thermal expansion, wear, and contamination. The oil galleries were large enough that partial blockages didn't matter. The cooling passages could handle significant scaling before performance degraded. The fuel system could cope with water contamination that would instantly destroy a common rail system. The legacy of these engines extends far beyond their racing success. They proved that absolute reliability could be a performance advantage. They showed that there was more than one way to win a race. While others focused on going fast and hoping to finish, Caterpillar engines finished and let speed take care of itself. The influence can be seen in modern diesel development. The current generation of diesel pickup truck engines making 1,000 lb-ft of torque owe their existence to Caterpillar, proving that diesels could be performance engines. The reliability standards that we now expect, 200,000-mile warranties, 10,000-hour industrial ratings, were pioneered by Caterpillar's obsessive engineering, and even modern racing has learned from the Caterpillar approach. The diesel prototypes that dominated Le Mans in the 2000s and 2010s, the Audi R10, Peugeot 908, Toyota TS040, all used design principles established by those Bulldozer engines. They ran lower specific outputs than gasoline engines but made up for it with consistency and fuel efficiency. The technical specifications of these engines remain impressive even by modern standards. The 3406 that raced at Le Mans had pistons the size of coffee cans. Each one weighed 8 pounds. The connecting rods were over 2 inches thick at the beam. The head bolts were essentially construction-grade threaded rod torqued to 350 lb-ft. The fuel injectors could survive being hit with a hammer. Teams actually tested this. The materials science was equally impressive. Caterpillar developed their own aluminum alloy for pistons that maintained strength at temperatures where other alloys turned to putty. They created surface treatments for cylinder liners that reduced wear rates to almost nothing. They pioneered the use of synthetic oils when everyone else thought mineral oil was good enough. The manufacturing processes were revolutionary. Caterpillar was one of the first to use statistical process control in engine production. Every dimension on every component was measured and recorded. They could trace a failed part back to the specific tool that machined it, the operator who ran the machine, even the batch of raw material it came from. This obsessive quality control meant that reliability wasn't luck, it was guaranteed. And modern Caterpillar engines have evolved, but the philosophy remains. The current C32 V12 makes over 2,000 horsepower in marine racing trim. It can do it for thousands of hours. The latest C175 V20 makes 4,000 horsepower and is designed for 50,000 hours between major overhauls. That's nearly 6 years of continuous operation. But the story of Caterpillar engines in competition isn't just about the machinery. It's about a different way of thinking. While everyone else was asking Hark, how fast can we go? Caterpillar was asking Host, how long can we last? While others chased the theoretical limits of specific output, Caterpillar chased the theoretical limits of durability. They proved that, in the real world, the tortoise really can beat the hare. Now, the engines that started life pushing dirt and hauling freight became unlikely racing legends not by being the fastest or the most powerful, but by being the last ones running when the checkered flag fell. They proved that sometimes the best engineering isn't about doing more with less. It's about doing exactly what's needed, reliably, consistently, forever. In an age where we celebrate efficiency and optimization, there's something magnificent about an engine that weighs a ton, makes modest power, and absolutely refuses to break. It's a reminder that engineering excellence comes in many forms. Sometimes it's a screaming Formula One engine that makes 1,000 horsepower from 1.6 liters. And sometimes it's a Bulldozer engine that makes 400 horsepower from 14 liters and will still be doing it long after the F1 engine is scrap metal. The next time you see a piece of Caterpillar equipment working on a construction site, remember that inside that machine beats the heart of an unlikely racing champion. An engine built not to win on outright speed, but to win by simply refusing to lose. An engine that proved that in the harsh arithmetic of endurance racing, reliability multiplied by time equals victory. What's the most impressive feat of engineering reliability you've ever witnessed? Drop a comment below and let me know. And if you want to hear more stories about unlikely racing heroes and the engineering that made them legendary, make sure to hit that subscribe button. Until next time, remember, speed wins races, but reliability wins championships.